4-bit sum out and a carry out. So if I was going to write down the module statement for this, I would have module, and let's call it full add. And then for the port list, I would have A, B, sum, carry in, carry out, and then I would have the declarations and so forth for the module template. Now let's suppose that you want to simulate this particular design. And I'm going to call this module top. This is your test bench. And you recall that the test bench is that particular module where you define what test patterns you're going to apply to test this particular design when it's being simulated. The module statement for top, which is the name of my test bench, looks like that. And you'll notice there's no port list. Why do you think that's true? Why would a test bench have no port list?
But first then, so there's nothing that would be giving you anything?
Okay. These signals that you have listed here in your port list are external signals coming in and signals that go out. But your test bench, where you're generating your test patterns, is the highest priority, or the highest in the hierarchy, I should say. So when you set this thing up in the module top, you would have a statement where you instantiate this design into the test bench. So your test bench will have instantiated in it all of the signals, all of the modules that are part of that simulation. And since this is the highest level of the hierarchy, there's no port list. So if you see a module declaration statement like this and there's no port list, that's your test bench. Okay. And this naturally creates a hierarchy like that. Okay. So I did want to cover that because you may encounter this where there's no port list. I wanted to explain what that was.
Is there a way to add external buttons into Verilog? Like physical hardware switches?
No. You can define the signals that would be generated by the switches, but you can't. There's no module that you could declare for say a single pole, single throw switch of some sort.
Right.
So I want to start out with the definition of abstraction. This is providing information while hiding the details. This is along this notion of you can't see the forest for the trees. I can explain something to you without going into a lot of detail, because the detail would just clutter up the explanation. So we'll get rid of the details that are unnecessary so that we can concentrate on a major concept. And so when you do an abstraction, you're hiding the underlying details. So if there is high abstraction, there are a few details. And with low abstraction, you have many details. Now, the reason we're talking about abstraction is there are many different ways that I could describe a digital circuit with different levels of abstraction. The more details you provide, the less that you rely on the synthesizer to figure out how to implement your circuit. So if I have a description of a circuit and I'm using high abstraction, the synthesizer's got to figure out a lot on its own on how to implement your circuit. If I provide a low abstraction description, I'm providing many details, and there's very little for the synthesizer to figure out. Now, this isn't exactly the way that Verilog will do it, but this will give you an idea of what I mean by the different levels of abstraction that you could use to describe a design and what the synthesizer might have to figure out. Let's suppose I had the following circuit. Okay, I could give you a schematic. And you could see that I'm telling you what kind of gates to use and what kind of interconnections between those gates there should be to form the circuit. Or I could do this equivalently. I could give you a Boolean expression. Now, I'm not telling you what gates to use, but I am telling you how to implement it through some mathematical expression. I think you could see that the synthesizer would have to figure out for this simple Boolean expression how to actually implement it. Here I'm telling the synthesizer what gates to use and how to interconnect them. The synthesizer would have to figure that out. Here I'm just giving you a truth table. And all the truth table tells you is the input-output relationships. It doesn't tell you anything about how to implement it. It just tells you input-output relationships. So, as I move from left to right, I'm providing a higher level of abstraction. And the synthesizer's got to figure more out on how to implement the circuit as I get to higher and higher levels of abstraction. But either one of these three forms correctly describes the same digital circuit. Okay. All right. It turns out that in Verilog, there are three levels, there's actually 4 levels of abstraction in Verilog. If you look at the IEEE 1364 standard. At the switch level, all you're doing is telling the synthesizer how to implement the circuit at the switching transistor level. You're actually specifying MOSFET transistors and how they're connected to create different types of gates. And from there, you could build up your circuit. The gate level, as the name implies, I'm specifying specific logic gates, and then I've got to have some syntax to tell you how to interconnect those logic gates. The data flow, you're giving Boolean expressions, and at the behavioral level, you have high-level programming constructs. For loops, while loops, if then else statements. C has a switch statement. In Verilog, it's called a case statement, but it's semantically the same. So I'm going up in the levels of abstraction as I work my way from 1 to 4. Now this one we're not going to worry about. In this class we're just going to deal with these 3. Now the key here is I want you to focus in on writing synthesizable code. I will show you some examples of Verilog code that is not synthesizable, and you should avoid putting that syntax in the Verilog programs that you write. Now, what would happen if you happen to put non-synthesizable code in your description and then try to synthesize it? Well, the answer is it depends. For some syntax, like the case equality and case inequality operators, the synthesizer would probably generate an error and exit, because that particular operation is not synthesizable. There are other types of syntax, which we will see, some of them today, where the synthesizer just ignores them, as if you didn't put them in. It may generate a warning, but it will not generate an error, it will not kick out your design. Incidentally, for the non-synthesizable syntax, it is all simulatable. So if you put this into a simulator, the simulator will work perfectly. But not all code is synthesizable. But we'll see that as we go along. So the first level of abstraction that we want to deal with is in chapter 5, and that's going to be the gate level. And we're finally going to get to the point in the course where we are going to describe actual Verilog programs that describe digital designs. So the gate level of abstraction is the lowest level. And it has the greatest chance of being synthesized. Correct. Why do you think that's so?
Because the synthesizer has to figure out very little.
I can't.
The synthesizer doesn't have to figure very much out, and you're gonna
Precisely. We are going to tell the synthesizer precisely what kind of gates to use. Now, the synthesizer is going to have to figure out some things, but when we get to that point, I'll give you an example of something a synthesizer might have to figure out, despite the fact I'm going to describe my design in terms of gates and how those gates are interconnected. In fact, let me give you an example right now. Let's suppose that's what I want. And in my Verilog code, I specify a 3 input AND gate function. But let's suppose that your component library only has 2 input AND gates. Then the synthesizer would have to figure out that it needs to do that to get a 3 input AND gate function. Because the synthesizer can only use what's in the component library, and if you only have 2 input AND gates in the component library, but you need a 3 input AND gate function, then it's gonna have to figure out, using 2 input AND gates, how do I construct a 3 input AND gate, and that's what the synthesizer would have to figure out, yeah.
And does that, does it also like change the timing for you? Because let's say you have, time specs that you need to meet, and by adding another gate, you can add more propagation delay. Does it also?
Well, the synthesizer would not necessarily figure out what the timing is. There are design automation tools that estimate the timing based on what got synthesized. So once the synthesizer outputs that gate level net list, now you can have a tool that can go in and say, okay, I now know how the synthesizer did it. Let me go ahead and figure out what the timing should be. Gate primitive. This is a predefined logic gate. In Verilog. Yes?
Your previous slide said that the gate level had the highest chance of being synthesized correctly, which, does that mean that there's a chance that the synthesizer will not be able to figure out some valid gate level designs?
Now, you determine what level of abstraction you're gonna use, and the synthesizer will use whatever you provided to produce the design.
But you said that it had the greatest chance of being correctly synthesizable, which implies that there's a chance that it cannot be correctly synthesized.
There's always that chance when you deal with the higher levels of abstraction.
So we don't have a guarantee that the synthesizer will actually do the thing and actually synthesize the design properly?
Well, I think we're getting in the weeds here. When I say correctly synthesized, what I'm talking about is with the most efficient type of circuit in terms of gate count.
Sorry, like that, in that same kind of logic constraint, if I wanted it to synthesize, some sort of circuit, I give it a gate level list, but in my component list, I only allow it to use OR gates or something like that, and it's not able to do that? Do you understand? Like, will that then?
Oh, what
spit out
happens
error?
if the component library doesn't have the right kind of devices?
Yeah, if it's,
Okay, let's differentiate between two things. If we're talking about an ASIC design, that ASIC library will have the basic types of gates in the component library. So you'll always have, at an absolute minimum, 2 input NAND gates.
Yep.
So I can always implement a circuit solely out of 2 input NAND gates, or 2 input NOR gates. For FPGAs, as we're gonna find out, that really doesn't work off of gates, because Boolean logic is actually implemented in lookup tables. But we'll get into that when we start to look at the architecture of some field programmer Gator is. So, Verilog has some predefined logic gates so that you don't have to write a module on what is an AND function, what is an exclusive OR function, and so forth. And so these are the predefined gates, the gate primitives for Verilog. Up here you see the keywords, and again, remember keywords are always lowercase. And here's the corresponding gate. Now, as far as the syntax is concerned, for these gates, is you will have the gate type, and this could be and, or, and so on. A gate identifier, and this is actually optional. But highly recommended. And then the port list.